Imagine a magic box. You drop a number into an input slot, something happens inside, and exactly one number pops out of the output slot. That box is a function. It's a rule that takes an input, does something to it, and gives back exactly one output. For example, if the rule is add 2, then when you put in 3, you get out 5. We write this as f of x equals x plus 2. The def is just the name of the box, and the x is whatever you put in. Why do we care about a box that turns numbers into other numbers? Because the world is full of relationships where one thing depends on another. If you know the rule, you can predict what will happen. How far does a car go if you drive for 2 hours at a steady speed? That's a function. Distance depends on time. In calculus, we study how these outputs change when the input changes, how fast, how steeply. A function is the basic object we analyze. It's the story we're telling, and calculus is the grammar we use to understand it. Let's open the box. The domain is the set of all numbers you're allowed to put in. For f of x equals x plus 2, you can put in any number, so the domain is all real numbers. But for a function like f of x equals 1 over x, you can't put in 0, because dividing by 0 is undefined. The range is the set of all numbers that can come out. For f of x equals x plus 2, the range is also all real numbers. Now, how do you know if a graph is a function? Use the vertical line test. If you can draw a vertical line anywhere and it hits the graph more than once, then one input gives multiple outputs, and it's not a function. A circle fails this test, but a straight line passes. Let's solve a real problem. Imagine apples cost 3 rupees each. The total cost is a function of the number of apples you buy. We can write this as C of n equals 3n, where n is the number of apples. The domain is all whole numbers, you can't buy half an apple. The range is multiples of 3. Now, if you buy 5 apples, what's the cost? We just plug 5 into our function, C of 5 equals 3 times 5, which is 15 rupees. The rule gives exactly one output for that input. This same idea, a rule turning an input into an output, is how we model everything from bank interest to the path of a rocket. Imagine a long, straight road stretching out forever in both directions. We call this the number line. Right in the middle, we put a special mark and label it 0. 0 is like home base, it's the starting point. Now, every step you take to the right lands on a positive number, 1, 2, 3, and so on. Every step to the left lands on a negative number, -1, -2, -3. The number line is just a way to lay all numbers out in order, so we can see where they live relative to 0. Why do we even draw numbers on a line? Because it turns abstract ideas into something we can see. When you know a function's domain and range, you can plot them on a number line and instantly see which numbers are allowed in and which come out. The line also gives every number a sign, a label that tells you which side of 0 it's on. Positive numbers are to the right, negative to the left. This sign is like a compass direction, it tells you whether you're moving forward or backward from 0. Without the number line, sign is just a symbol. With it, sign becomes a place you can point to. Let's build this from something simpler, a ruler. A ruler starts at 0 and goes only one way. The number line just extends that ruler in both directions. We take 0 as the neutral point, it has no sign, it's neither positive nor negative. Then we agree, every number to the right of 0 gets a plus sign, whether we write it or not. Every number to the left gets a minus sign. The sign isn't a separate thing, it's just the name for which side of 0 the number lives on. Think of it like a street address, the sign tells you whether you live on the east side or the west side of Main Street. That's why we call it that sign I of a number. It's the number's signature, its identity marker. Let's solve a concrete everyday problem. Imagine it's a cold morning and the thermometer reads -5 degrees Celsius. What does that mean? 0 degrees is the freezing point of water, our reference. -5 means the temperature is 5 degrees below freezing. On the number line, we'd place a point 5 steps to the left of 0. Now, by noon, the temperature rises to +3 degrees. That's 3 steps to the right of 0. The sign changed from minus to plus because we crossed the boundary. This same idea works for money. A bank balance of -200 rupees means you owe money, you're 200 to the left of 0. A balance of +500 means you have money, 500 to the right. The number line gives every quantity a home, and the sign tells you instantly whether you're above or below the reference point. Imagine you have a number like 5 or -3. You already know these numbers have a sign, positive, negative, or 0. The Signum function, written as Sgn of x, is a simple machine that looks at any number you feed it and tells you only its sign. It completely ignores how big the number is. If the number is positive, it gives back a +1. If it's negative, it gives back a -1. And if it's exactly 0, it gives back 0. So 5 and 100 both just become +1. It's like a sign detector that strips away all the size information. Why would we want a function that throws away the size of a number? Think about a car moving on a straight road. Sometimes you don't care about its speed, you only care about its direction. Is it going forward or backward? The Signum function answers exactly that question. In physics, it can tell you the direction of a force. In math, it's a building block for more complex functions that behave differently for positive and negative inputs. It lets us separate a number into two parts, its sign, which is the direction, and its magnitude, which is the size. This idea of splitting a problem into cases based on the sign is a powerful way of thinking. Since the output depends on which part of the number line the input comes from, we write the Signum function using what's called piecewise notation. This just means we define it in separate pieces, or cases. We say, if x is greater than 0, the output is +1. If x is exactly 0, the output is 0. And if x is less than 0, the output is -1. You can picture this as a decision tree. The function first asks, is the number positive? If yes, answer +1. If not, it asks, is it 0? If yes, answer 0. The only remaining possibility is that it's negative, so the answer is -1. This three-branch logic comes directly from our earlier idea of the number line being split into positive numbers, 0, and negative numbers. Let's use the Signum function in a real situation. Imagine you check your bank balance. Last month it was 200 rupees, and this month it's 150 rupees. You want to know the direction of the change, not the amount. First, we find the change, the new balance minus the old balance. That's 150 minus 200, which equals -50 rupees. Now we apply the Signum function to this change. Since -50 is less than 0, the Signum function outputs -1. This tells us the balance moved in the negative direction, it went down. The actual amount of the drop, 50 rupees, is completely ignored. We only extracted the sign information. This same method works for any change. A rise gives +1, no change gives 0, and a fall gives -1. We already know the Signum function as a rule. It gives us 1 for any positive input, -1 for any negative input, and 0 for an input of 0. Now we're going to draw that rule on a coordinate plane so we can see its whole personality at once. Imagine a graph. For every positive x, no matter how small, the output y is always 1. So we draw a solid horizontal line stretching to the right, sitting at the height y equals 1. For every negative x, the output is always -1. That gives us a second solid horizontal line stretching to the left, at the height y equals -1. But what about exactly at x equals 0? The function's rule says the output is 0. We mark that single, special point with a solid dot right at the origin, where x is 0 and y is 0. Why do we draw it this carefully, with dots and holes? Because this picture answers a deep question: what happens exactly at the boundary between positive and negative? The graph makes the function's decision at 0 crystal clear. As you walk along the top line from the right, getting closer and closer to 0, you're at a steady height of 1. But the moment you arrive at 0 itself, you don't find 1. You find a hole, a missing point, and the function's value has jumped all the way down to the solid dot at 0. The same thing happens from the left, where the value jumps up from -1. This is our first visual encounter with a discontinuity, a break in the graph where you have to lift your pencil off the paper. It shows us, in one clean picture, that the value a function is heading towards is not always the value it actually takes. Let's build this graph step by step from the piecewise definition we already know. The definition breaks the number line into 3 separate pieces, and we draw each piece on the same coordinate plane. First piece, for x greater than 0, the output is 1. On a graph, this is a horizontal line at y equals 1, but only for positive x values. It starts just to the right of the y-axis and goes on forever to the right. Since x cannot be exactly 0 in this piece, we mark its starting point with an empty hole at 0, 1. Second piece, for x less than 0, the output is -1. This is a horizontal line at y equals -1 only for negative x values. It goes forever to the left, and we mark its endpoint with another empty hole at 0, 1. The third piece is the loneliest, only for x exactly equal to 0, the output is 0. This is just a single, isolated point. Let's use our graph to solve a concrete problem. Suppose you're given the Signum function's graph and asked to find the value of SGN of 2, SGN of -3, and SGN of 0, just by looking. You put your finger on the x-axis at 2. You go straight up. You hit the solid top line at a height of 1. So SGN of 2 is 1. Now put your finger at -3. Go straight up, and you hit the solid bottom line at a height of -1. So SGN of -3 is -1. Finally, put your finger exactly at 0. Go straight up, and you land right on the lonely solid dot at the origin. The height there is 0. So SGN of 0 is 0. The graph makes these answers instant. Think of it like a 3-position switch, up for positive, down for negative, and a special middle position for exactly 0. The empty holes are the switched contacts that are deliberately not connected in the middle position. You already know the Signum function tells us the sign of a number. Now we meet its close cousin, the absolute value function, written as f of x equals the absolute value of xt. Think of it as a distance from 0's machine. If you put in 3, it gives 3. Put in -3, it also gives 3, because -3 is 3 steps from 0 on the number line. When we draw this, we get a V-shaped graph. The left arm slopes downward, the right arm slopes upward, and they meet at a sharp corner right at 0. That corner is where something interesting happens with the slope. In calculus, we care a lot about how far something changes, that's the slope, or derivative. Imagine walking along this V-shaped graph. On the left side, for any negative x, every step right makes you go 1 step down. The slope is -1. On the right side, for any positive x, every step right makes you go one step up. The slope is +1. But what about exactly at x equals 0? You're at the sharp corner. If you approach from the left, the slope is -1. From the right, it's +1. They don't match, so there is no single slope at that point. The derivative does not exist at the corner. This shows that not every function is smooth everywhere. Now here's the beautiful connection. The derivative of the absolute value function, for every x not equal to 0, is exactly the signum function. Remember, Sgn of x is -1 for negative x, 0 at x equals 0, and +1 for positive x. But wait, the derivative of the absolute value doesn't exist at 0, while Sgn of 0 is defined as 0. So the derivative of absolute value is Sgn of x, except we must leave a hole at x equals 0. This matches perfectly. The signum function's jump becomes a missing point in the derivative, reflecting the corner in the absolute value graph. It's a piecewise match made in calculus heaven. Imagine a car driving on a straight road. We track its distance from home. It drives toward home, passes it, and keeps going. The distance from home is like the absolute value function. It decreases to 0, then increases. The speed is how fast that distance changes, the derivative. Before home, the car approaches, so distance shrinks, speed is negative, say -30 miles per hour. After passing, distance grows, speed is +30 miles per hour. Exactly at home, the car changes direction instantly. The speed at that instant is undefined, you can't say if it's coming or going. The signum function tells us the direction of travel, -1 for approaching, +1 for leaving. So the derivative of distance gives the direction of motion, except at the turnaround. We already know the signum function, Sgn of x, gives us the sign of a number. But think of it less as a math fact and more as a tiny decision maker. You feed it any number, or a speed, a voltage, a temperature difference, and it instantly tells you which of three camps that number belongs to, positive, negative, or exactly 0. It strips away the size and keeps only the direction, or what engineers call the polarity. So Sgn of 5 is 1, Sgn of -3.2 is -1, and Sgn of 0 is 0. It's a compass that points only forward, backward, or to still. Why do we care about this simple compass? Because in the real world, we constantly need to answer one question: which way? Imagine a robot arm. Its motor gets a voltage. We don't just need to know how strong the voltage is, we need to know its sign to tell the motor to spin clockwise or counterclockwise. Or think of a car. A computer logs its velocity. Positive means moving forward, negative means reversing. The signum function is the perfect tool to instantly read that velocity data and decide, is the car going forward or backward? It takes a messy, changing signal and turns it into a clean, three-state command: on, off, or reverse. This is the core idea behind countless switches and control systems. Let's see this in action. Picture a car moving along a straight road. We plot its velocity over time. For the first few seconds, the velocity is positive, say a steady +5 meters per second. The car is moving forward. Then the driver brakes, comes to a brief stop where velocity is 0, and then starts reversing, giving a negative velocity, like -3 meters per second. Now, we feed this entire velocity graph into our signum function. What comes out is not a smooth line, but a square wave. As long as the velocity is positive, the output is a flat +1, meaning forward. At the exact moment of the stop, it drops to 0. And as soon as the car reverses, the output jumps to a flat -1, meaning reverse. We've just turned a physical motion into a clean digital state. Let's solve a concrete everyday problem, a smart thermostat. Its goal is to keep a room at exactly 21 degrees Celsius. The thermostat constantly measures the actual temperature. First, it calculates the error, actual temperature minus the target of 21. If the room is at 19 degrees, the error is -2. If it's 23 degrees, the error is +2. Now, we apply our Signum function to this error. If the error is negative, Sgn gives -1, and the thermostat switches the heater on. If the error is positive, Sgn gives +1, and it switches the cooler on. If the error is exactly 0, Sgn gives 0, and the system stays OFF. So, a single function, Sgn of the error, acts as the brain of the entire heating and cooling system, turning a temperature reading into a three-state command: heat, off, or cool. The whole idea is that Sgn, X, is a universal polarity detector, turning any continuous measurement into a simple, actionable direction. We've built up the Signum function, piece by piece. Think of it as a simple sign detector. You feed it any real number, and it instantly tells you the number sign. It spits out exactly +1 if the input is positive, 0 if the input is 0, and -1 if the input is negative. That's its whole job. We write this as a piecewise function, a single rule broken into 3 clear cases, one for each possible sign of the input. It's a tiny machine with only 3 possible answers. Why do we care about such a simple function? Because it captures the pure idea of direction, separate from size. In physics, it tells you which way something is moving. In engineering, it's the core of a switch, deciding whether a system should push left or right. We also saw its deep link to the absolute value function. The Signum function is like the derivative of the absolute value, giving the slope everywhere except at the sharp corner. This makes it a fundamental building block for more advanced ideas, like step functions that turn things on and off, and the very heart of control theory, where systems constantly make decisions based on the sign of an error. Let's see how this all fits together. We started with the number line, where every number has a home. The Signum function simply asks, which side of 0 are you on? This gives us the piecewise rule. When we graph it, we get 2 flat rays and a lonely point at the origin. The ray for positive input sits at a height of +1, and the ray for negative input sits at -1. At exactly 0, the output is 0, shown by a single solid dot. The jump between -1 and +1 creates a discontinuity, a break in the graph. We mark the endpoints of the rays with open holes to show they don't include 0, while the solid dot at the origin claims that single point. Let's put this to work. Imagine a simple room heater that only knows full on or full off. We want the room at 20 degrees Celsius. The heater measures the actual temperature, say 18 degrees. The error signal is the desired temperature minus the actual, so 20 minus 18, which is +2. The Signum function takes this error and outputs +1. The heater's control system reads that +1 and switches fully on. If the room overheats to 21 degrees, the error becomes 20 minus 21, which is -1. The Signum function now outputs -1, and the heater switches fully off. The Signum function is the decision maker, turning a continuous error into a simple binary command, heat or don't heat. So the whole idea is that the Signum function is a simple sign-to-action translator, a fundamental switch that forms the basis of all decision-making in systems.